Dear family of forensic chemistry and toxicology science, welcome to our channel. In our last lesson, we saw the introduction. For today, we will try to see the definition as well as the contribution of forensic chemistry and toxicology science in the criminal process and what the historical background is like. Have a great time. Forensic chemistry is a specialized branch of chemistry that applies scientific principles, techniques, and instrumentation to the analysis of non-biological physical evidence collected from crime scene or related to legal investigations. It focuses on identifying, characterizing, and quantifying unknown substances or materials to provide objective evidence that can be used in courts. Unlike general chemistry, which explores broad chemical properties and reactions for scientific or industrial purposes, forensic chemistry is specifically tailored to legal contexts, emphasizing chain of custody, reproducibility, and admissibility in judicial proceedings. This field often involves examining trace evidence such as drugs, explosives, poisons, fibers, glass, paints, and gunshot residues, using methods like chromatography, spectroscopy, and mass spectrometry to determine their composition and origin. Forensic chemists must work with precision, as their finding can directly influence the outcome of criminal cases, requiring not only technical expertise but also an understanding of legal standards to ensure evidence is handled and presented appropriately. At its core, forensic chemistry bridges the gap between laboratory science and law enforcement by transforming raw materials into actionable insights. For instance, it can be distinguished between substances that appear similar but have different chemical profiles, such as identifying whether a powder is an illegal drug or a harmless compound. This analytical process typically begins with qualitative examination, for example, using microscopy or spot tests to confirm the presence of certain elements, followed by quantitative analysis to measure concentrations or match samples to known standards. The discipline draws from subfields like analytical chemistry, toxicology, and material science, making it interdisciplinary and adaptability to various types of investigations. Forensic chemistry plays a pivotal role in the criminal justice system by providing reliable scientific evidence that supports investigations, prosecutions, and defenses. It helps establish facts in criminal cases, such as linking a suspect to a crime scene through chemical matches or determining the cause of death via toxicological analysis. In practice, forensic chemists work primarily in government or private laboratories, collaborating with law enforcement agencies like the FBI, local police, or medical examiners to process evidence collected from scenes of crimes, accidents, or suspicious deaths. Their analysis can exonerate the innocent, convict the guilty, or clarify ambiguous circumstances, thereby enhancing the efficiency and accuracy of crime solving. One key role is in drug-related cases, where chemists identify controlled substances, quantify purity levels, and trace manufacturing origins, which is essential for building cases against traffickers or users. In arson investigation, they detect accelerants like gasoline in fire debris to distinguish between accidental and intentional fires. Toxicology, a subset of forensic chemistry, examines bodily fluids for poisons, drugs, or alcohol, often determining if impairment contributed to a crime or death. Beyond analysis, forensic chemists prepare detailed reports and may serve as expert witness in courts, explaining complex scientific concepts to judges and juries in a clear and unbiased manner. This testimony can be decisive as courts increasingly rely on empirical evidence over circumstantial accounts. The integration of forensic chemistry into the justice system also promotes fairness by adhering to standards like those outlined in the federal rules of evidence, ensuring that only relevant and non-prejudicial scientific data is admitted. However, challenges exist, such as backlogs in labs, the need for ongoing training in emerging technologies, and ensuring the integrity of evidence chains to prevent miscarriages of justice. Overall, forensic chemistry strengthens the system's credibility by grounding decisions in science, reducing reliance on eyewitness testimony, which can be fallible, and aiding in the resolution of cold cases through reanalysis with advanced tools. The development of forensic science, including forensic chemistry, has evolved from rudimentary observations in ancient times to a sophisticated multidisciplinary field today. While forensic chemistry as a distinct discipline emerged in the 19th and 20th centuries, its roots intertwine with broader forensic advancements. Below is a discussion of key historical milestones, highlighting how they paved the way for modern practices. Ancient origins, pre-1000 AD. Evidence of forensic-like practices dates back to antiquity. Around 200 BC, Babylonians used fingerprints on clay tablets for business transactions, marking one of the earliest uses of biometric identification. In China during the Qin dynasty, around 221 up to 206 BC, fingerprints were similarly employed for official documents. A seminal milestone came in 1248 AD with Songxi's collected cases of injustice rectified, or also known as washing away of wrongs, the first known text on forensic medicine. It detailed autopsy procedures, signs of death, and insect activities on corpses, introducing systematic approaches to determining causes of death, which influenced early chemical analysis of poisons. In 80s up to 19th century emergence of chemical detection methods, the Enlightenment era shifted investigation towards evidence-based rationality. In 1773, a Swedish chemist Carl Wilhelm Scheele developed a method to detect arsenic in corpses, revolutionizing toxicology and enabling the identification of poisons in murder cases, a foundational step for forensic chemistry. By 1813, Mathieu Orfila, often called the father of toxicology, published Trait des Poisons, systematizing the study of poisons and their effects, and testifying in courts using chemical evidence. The 19th century also saw advancements in fingerprinting. In 1892, Sir Francis Galton published a classification system for fingerprints, building on earlier work by Henry Fauld's and Wilhelm Scheele, which became a cornerstone of forensic identification. Early 20th century institutionalization and technological advances. In 1901, Scotland Yard established the first fingerprint bureau in England, formalizing dactyloscopy. Edmond Locard's exchange principles in 1910, that every contact leaves a trace, became a fundamental concept, emphasizing trace evidence analysis central to forensic chemistry. The 1930s brought the establishment of forensic laboratories, like the FBI's lab in 1932, which integrated chemical analysis tools. Post-World War II, techniques like tape lifting for fingerprints and voice print identification emerged. Mid to late 20th century, DNA and modern innovations. The 1953 discovery of DNA's double helix structure by James Watson and Francis Crick laid the groundwork for genetic forensics. In 1984, Sir Alec Jeffreys developed DNA fingerprinting, first used in a 1987 case to exonerate a suspect and convict the real perpetrator. The 1970s introduced the FBI's Automated Fingerprint Identification System, or AFIS, in 1977, and by the 1980s up to 1990s, methods like restriction fragment length polymorphism, or RFLP, and polymerase chain reaction, or PCR enabled DNA profiling from minute samples. 21st century digital and interdisciplinary growth. Recent milestones include the 2009 National Academy of Science report critiquing forensic practices, leading to reform for greater scientific rigor. Advances in mass spectrometry and AI-driven analysis have enhanced chemical detection, while global databases like CODIS or Combined DNA Index System facilitate cross-jurisdictional investigations. The field continues to evolve, addressing challenges like digital forensics and environmental crimes. This milestone illustrates how forensic science transitioned from anecdotal methods to evidence-driven discipline, with forensic chemistry emerging as a critical component for chemical-specific insights. This progression has not only improved investigative accuracy, but also highlighted the need for ongoing ethical and scientific standards to prevent errors.